All right, welcome back. I got turn 10, so let's go ahead and get back into it. One thing I want to remind you of, I just put an announcement on Canvas like very recently, but I have tests to give back to you. So if you want yours back, stick around or come see me in office hours and I'll have it. Okay, so a few days ago, we started this idea of, you know, using these geometric sums as a means to build up a power series or as a means to represent a function as a power series. So what we're doing now to extend that is instead of really just relying on that geometric sum, maybe we can open up a few more avenues to us if we see the function represented as the derivative or the integral of something that looks like the geometric sum. So the function I gave you all last time was this 1 over 1 minus x squared, which might be difficult or maybe impossible to represent as a power series, but we can use a derivative. So one thing we reminded ourselves of last time is that the derivative of 1 over 1 minus x is equal to 1 over 1 minus x squared, which is the series we're looking at. So where we left off last time, I believe, is this. We can turn 1 over 1 minus x into a power series, right? Because can we represent 1 over 1 minus x as a geometric series? Or as the sum of a geometric series? So first term 1, common ratio r. That gives us this power series. The sum from n equals 0 to infinity of x to the power of n. So this right here is a power series for 1 over 1 minus x. But how is 1 over 1 minus x related to, can't erase that, related to the thing we actually want to find a power series for? Which is 1 over the quantity 1 minus x squared. Is the rate of change the derivative of it, right? So basically, what do we need to do to this power series? So let me write a couple things out here. I wish I could erase the things I've already done. But here's what we know. We know that 1 over 1 minus x is equal to this. 1 plus x squared plus x cubed, and so on. So what we really care about, though, is this, 1 over 1 minus x all squared. So how do I get from the series that I've written out on top to this series below it? I think that's going to go the opposite direction. Because remember, the derivative of 1 over 1 minus x is 1 over 1 minus x squared.
Yeah, I thought we were going back to 1.
Oh, so no, sorry. I'm going from the thing I know to the thing I want. Because here's kind of like to reset the stage. So the bottom line kind of goal here is I want to take a function and represent it as a power series. Until very recently, the only real way I had to do that was to somehow make that function look like this, which is the sum of a geometric series. But now we have a little more leeway because even though 1 over 1 minus x squared doesn't really look like that because that 1 minus x is contained in parentheses, if I can think about what the derivative of that looks like or what the integral of that looks like, maybe that will look like a geometric series and I can kind of go back and forth. So this is something we did last time. We took the integral of this function, 1 minus x to the negative 2, and that came out to be 1 over 1 minus x. Does this thing fit the mold of a sum of geometric series? That does. So if we can like do all of our manipulations with that, and then kind of undo the calculus, so basically undo that integral, we can get the power series we actually want. So that's sort of what we've done. And in whatever space I have left, maybe I can kind of do a flow chart here. So what did we do with f? We found the integral of f, right? And then we turned that into, you know, a power series, right? So a power series from n to infinity of, you know, c naught x to the, or cn x to the n. And I think we've done these first three steps, right? I gave you a function, we integrated it, and we turned that integral into a power series. So now what do I have to do with that power series to get what I actually want? I'm going to take the derivative of this power series. That's the point. So basically, I'm trying to come up with the, I wish I had a better way to kind of like to visualize it. So basically, so here's the function we start with, right? I took the antiderivative of it, did all my power series analysis with it, but all the stuff that I'm like doing all the power series work with is not the thing I care about.
So when you took the derivative, you don't really need that one, or what do you?
No, so trying to think of a diagram I could throw at you here. And if I could, what space I would actually put it in. Maybe let's do this. This kind of scares me, but we're going to do it. It's weird. Okay, so basically think about this as we have two different levels here. I have my function, and I have the integral. So the function is the thing I care about, right? But the function is not in a form where I can treat it as the sum, like as the sum of a geometric series. So it doesn't have it. No, not the square. I mean, the square is part of the problem, but what's the real issue? What's that? Yeah, I think that's basically what's going on here is that I don't have like in the sum of a geometric series, it's first term divided by 1 minus r, where like I have those two terms are distinct. I mean, the square, it's not the square in and of itself is the problem, but what am I squaring here? I'm squaring that whole 1 minus x, that whole quantity.
It's not, so it's because it's like bigger than the 1 minus x?
Yeah, so let me give you another example here. If I had another function g equals 1 over 1 minus x squared like this, could I treat that as the sum of a geometric series? I can do that directly because basically, how are the 1 and the x squared related? I'm just subtracting them. How are the 1 and the, so basically, the square involves the 1 in the thing that we're actually dealing with. So because of it, the function we have is not something I can do power series analysis with. So basically, I have to basically look at capital F, basically the integral of this function, and turn that into a power series of F. Because the integral of F is this thing. That's this, basically this right here I can call capital F. Which directly fits this sum of a geometric series. So because that exists, basically it's much easier for us to take the integral of that function, capital F, and turn that into a power series because it's in a form that's a lot more conducive to do that with. But after I do that, do I have the thing that I really want? Because think about it, what I really want, kind of the finish line here is this. The finish line is I want a power series of lowercase f, right? So f is not in a place where I can easily make a power series of it, but capital F is. So I make a power series out of it. But how do I get from the power series of capital F to the power series of lowercase f? I take a derivative to undo the integration part. So it might seem like we're kind of like changing the game, and in a way we are, but we're doing it in a way that basically we're doing the analysis on an easier thing, and then basically undoing that to get to where we actually care about. So I believe that I gave you this lowercase f, we integrated it to find this capital F, and then we did the power series, which is written down below. So how do we get to the power series of lowercase f? Do the derivative, right? So what is the derivative of 1 plus x squared plus x cubed and so on? Right, it's going to have this form here. So, and one thing we talked about on Friday as well was, if you write down what the power series of a function is, and we said the power series of 1 over 1 minus x is equal to this. This power series of x to the n, right? So one other thing I want to point out here is that the power series representation of a function and the function, like, basically they're equivalent ways, but they're exactly identical. They're written differently, but they are the same. So this equal sign is not lying to you. These two things are equal, even though they look very, very different. So if this is true, then this must also be true. The derivative of 1 minus x that are equal to the derivative of this power series. So Clement just gave us the derivative of the first several terms of like the first few terms of the power series. But one thing we talked about is that you can directly take a derivative of the way the power series is defined, right? Go ahead, I'm sorry.
Why is it 1 minus x? No, 1 minus x to negative.
No, yeah, I just wrote it down wrong. Thank you. So what is the derivative? What is this new power series after I take the derivative? So a couple options here. You can either take a derivative of this thing like as it's written, or you can take the derivative of, or basically we have the derivative here in the first few terms. We can try to generalize that.
Minus x to the n minus 1.
How'd you get that?
It's the power rule for
Right. So maybe the first derivative rule you ever learned was how you take the derivative of x to the n. So that becomes n times x to the negative 1, which should fit the thing down below. So a lot to talk about. And I think, just based on the way things are going now and in times when I've taught this in the past, I think probably the big questions are why we have to do all this work with a thing that's like really not the target. But what questions do you have? How are we doing? Go ahead.
so they take the derivative. But if we're asking which problem, how would I know to do that?
That's a good question. So really, in fact, you brought up taking a derivative, so let's do it. The function we have is f equals, I'll rewrite it as 1 minus x to the negative 2. If that's the function, what is its derivative? Two times 1 minus x to the negative 3, or 2 over 1 minus x all cubed, right? So that derivative, and remember, like kind of our biggest tool in our arsenal here is that sum of a geometric series. Does that 2 over 1 minus x cubed match that? So yeah, you can try a derivative, but it's not, in this case, it's not gonna. What else? All right, should we look at another one? What about this thing? Is the natural log of 1 plus x a geometric series? Can't even imagine how I might. If you take this derivative, what told you derivative? So the derivative of a natural log term, like, kind of inherently gives you something of the form 1 over a function. So in this case, the derivative of natural log of 1 plus x should give me 1 over 1 plus x, right? And I got to worry about the chain rule, right? 1 over 1 plus x, what's the derivative of 1 plus x? Okay, so I think we're done. So the derivative of this is equal to 1 over 1 plus x. Is 1 over 1 plus x something I can think about as a geometric series? Cool. So let's start thinking about it that way then. So basically what we've done is this. We found that f prime of x is equal to 1 over 1 plus x. You all seem to agree that that can be the sum of a geometric series. So what does that geometric series look like? Maybe we should write down what the first term and the common ratio are. What is the first term? What's the common ratio? Negative x. So because of that, let's write out a few terms. First term 1, next term minus x, and then plus x squared minus x cubed plus x to the fourth. So we know something about the derivative of this thing and a power series that comes out of it. What else can we do with that? Do what? Right. So if we know this about, basically what I can do is, yeah, if these two functions are equal, I should be able to integrate both sides and get what? What's the integral of f prime of x? F of x equals what? I want to see out of this series. So I think I see a pattern emerging. Can I represent that as a power series? One thing we didn't do is this. We didn't like compact this series. But can we do that? If I try to capture all these terms, the 1 minus x plus x squared and stuff, into a sigma notation, how can I define that? Negative x to the n. How'd you do that?
defined by negative x, or you can just do the form of a times r raised to the power.
Right. So one thing I want to remind you of, and I think we said this on Friday, was that in general, these power series represented from functions is equal, like this geometric series is a times r to the power of n. So we know first term is 1, common ratio is negative x. I believe this representation holds. Now we have a couple different ways to get there, but what is what's the power series we care about? How can I define that? Negative x to the n over n. Not quite. Right, we have to raise the power by 1 and then divide by that new power. And because we're integrating, I will have a constant. Questions here? I also asked for the radius of convergence. How do I find that? We could. I don't think we need to for this kind of series. So I'll tell you that a ratio test would absolutely give it to you. We can do something a little more, actually a lot more simple in this case. Because what kind of series is this? It's geometric, right? We have a much better idea about how, I mean, the ratio test tries to force series to mimic a geometric sequence. This actually is geometric. So we can, what do we know about where geometric series converge? Where the ratio is between -1 and 1. So if the absolute value of negative x is less than 1, or equivalently, the absolute value of x is less than 1, or between -1 and 1. But this is the common ratio of the derivative of the series, right? Clement, questions?
That's some right, because if you have 0, negative x is a positive. Negative x to the power of 1 over 1.
Negative x to the power of 1 over 1. Yeah, you're right.
So should we pull out the -1 and have the negative plus the n?
Can we skip a term? Should there be a 0?
Yeah, when n equals 0, you get a negative x over 1, right?
Yeah.
So it is all by 1.
We pull out the -1, make it -1, and
Yeah, let's do that. So -1 to the n. No, that was the point I was going to bring up next, is that, so when we took a derivative, this thing is geometric. And we got this ratio from the geometric series, right? But can I say for sure that if I integrate, to go back to the natural log thing, what does that tell me with the ratio? It's like, do I still get the same radius of convergence after I integrate? So that actually is something we talked about last time. I'm not going to flip back because I think it's several slides ago, but if you have a series and you know its radius of convergence, then its derivative or its integral will have the same radius. So I do get that radius for free. So what is my radius of convergence? I wrote down the interval, but the radius is just a single number.
Why is it 1?
Good question. Why is it 1? Because I think this is a subtle and kind of a mysterious thing that comes up a lot. Why is the radius 1? It goes from -1 to 1 Let's think about circles. Circles is probably the first time you heard the word radius. What about a circle? Like, what does the radius mean in relation to circles? Half the what? Half a diameter? Or what else? This distance from the center out, right? And it's not a coincidence. That's basically what this radius convergence is. What's the center x value for which this thing converges? 0. How far can I be from 0 and still converge? 1. So that's the radius. Is basically how far from the center of your interval you still get convergence. But yeah, that's essentially what the radius is.
How did you look at this function and think one? Is it always be one, or is it kind of fit that?
I can show it to you graphically, and then I'll show you another example that's a little more complicated. So if my interval of convergence is between -1 and 1, I can, because how did I get that alternating series? To be fair, it was always alternating. Geometric series can alternate. That's okay. But so this ratio, and I think Sophie, this came from you, this absolute value of negative x being less than 1, that gives us this interval, right? So why am I allowed to rely on that interval after I integrated? That comes from a theorem we talked about on Friday, is that if you have a power series with some radius of convergence, you get that same radius even after you take a derivative work. So basically, a lot of the work you do, a lot of the work you do with the geometric series, you get to keep even after you integrate or differentiate away to something that's not geometric. So back to this idea. If we have -1 and 1 being the endpoints of our interval, what's the midpoint of those two things? Zero. They might have a different interval, but we're not actually checking for that right now. We're not checking the endpoints. We just know that everything inside this interval, -1 to 1, is going to converge. Let's do another thing here. Someone throw a number at me. 20 sounds good. Someone give me a negative number. -5. I'm going to cordon this off since this is totally unrelated to where I started, but I think this will help me kind of hopefully clear up some of the confusion people have with radius and interval convergence here. So basically, just randomly, you all gave me an interval of convergence. What's the radius of convergence that comes from this interval? How'd you get 12.5? How'd you find the total distance? So 20 minus -5, right? That is a diameter. We're so used to thinking about diameter as something that only a circle has. But do you know what the mathematical definition of a diameter is that's really general? It's just the furthest distance between any two things in like a set. So like, here's a weird example. If I draw you a shape like this, that has a diameter. And what the diameter means is basically, if you pick the 2 points that are furthest apart, the distance between those things is the diameter. So it's not always, it doesn't have to necessarily be a circle. And these intervals are kind of the same thing. What's the furthest point between two places in this interval? Well, it'll go from here to here, right? -5 to 20. That's 25. If that's the diameter, so what's the radius? I think we already said it. 25/2. 12.5. What's the center of this interval? 7.5. What is 7.5 plus 12.5? 20. What's 7.5 minus 12.5? -5. So hopefully that all kind of feels more consistent now. Questions? All right. Let's look at least one more of these. Want to find a power series representation for this thing. The inverse tangent of x. Very much not geometric, but can I get to something geometric by operating on it somehow? Yeah, that's a good question. Do you remember which way that goes? Yeah, so the something of tangent inverse tangent x is 1 over 1 plus x squared. That is the derivative. Not always. I think the very first one we did, we integrated first, right? So I think the first one we did was this, right? So it very much depends on what the nature of the function that I give you. So the derivative of the inverse tangent of x is 1 over 1 plus x squared. Is 1 over 1 plus x squared geometric? What's the first term? 1. Common ratio? Negative x squared. So because of that, I think I can say this: 1 over 1 plus x squared is equal to. Now you tell me, should I write out a few terms, or should I just write the sigma? Okay, give me some terms. 1 minus x squared. Okay. So first 5 terms like that. Now let's compact that into a sigma notation. What would that look like? Negative x squared to the n. Okay. So we've done a lot of work with the derivative, which is geometric. So then how do I find the power series for the function I actually want? Now I got to go the other way. Got to take the antiderivative. So the antiderivative of 1 over 1 plus x squared is inverse tangent of x. You want to integrate those terms, or you want to integrate the sigma notation? What is the integral of the sigma notation? Negative 1 to the n, we'll treat that like a constant because it very much is. I should actually write the sigma. One thing I will do is I'll rewrite this slightly as, let's pull out that negative 1 to the n. Negative 1 to the n times x squared to the n. What am I doing? Okay, so if I integrate, I got negative 1 to the n, and what's the rest of it? X to the 2n plus 1 divided by 2n plus 1. How we doing? Let's make sure that that works this time, because like we were off. Basically, we were alternating in the wrong way last time. If n equals 0, what do I get? X squared over, yeah, x squared, right? First term should be positive x squared. No, no. Okay, yeah, that makes sense. So the first term is just x, right? Is that if we were to integrate this one?
Yeah.
Your Calc 1 teacher would be very mad at me for forgetting this constant. So now that we have that power series representation, any questions there? Go ahead. Good question. Why is the R negative?
The form is A over 1 minus R.
1 minus R, and that's exactly it. So yep. So basically this is 1 over 1 minus negative x squared. All right. What would the radius of convergence be? How do I find that with these kinds of series? Right, so basically it comes from the common ratio. So I'll start there. I want the common ratio to be, or the absolute value of the common ratio to be less than 1, which means the absolute value of negative x squared is less than 1, which means the absolute value of positive x squared is less than 1, not equal 1, less than 1. Which I think we said a while ago, or maybe on Friday, was this is equivalent to the absolute value of x being less than 1. Yeah, absolutely. So let's start with that. The absolute value of x squared is less than 1. What does it mean for, what does the absolute value mean? Distance from 0, right? So basically I'm saying that the distance from x squared and 0 is 1 or less. So I mean, one way we could say it, it doesn't really make sense to write it as -1 is less than x squared, which is less than 1. But let's go with that verbal description for now. The absolute value of x squared is less than 1. That means basically the distance from x squared and 0. So as long as I'm saying like that, let's represent it that way. Basically, the distance between these two things, x squared and 0, is less than 1. For what values of x is that distance less than 1? What's that? Values of x that are less than 1. All the values? What about -2? Right. So that's the point here, is that if you're too far from x on the negative side, that inequality fails. So I think one thing that kind of makes this kind of confounding is the fact that in the few times this square root thing has come up, it's been 1. But let me modify this a little bit. What if, for whatever reason, and again, I'll block this off, we got absolute value of x squared is less than 100. What's that? That's what I was trying to get to is, yes, what does that mean? That means the absolute value of x is less than 10.
So you can do all for that, the other equations with the absolute values over here.
I wouldn't say all, but in this case, yeah.
Absolutely. So we say the root of -100. And
the root of -100, yes. But if we're only looking at real numbers, basically, if I say the absolute value of x squared is less than 100, I think that more intuitively means that x is less than 10, right? But are there negative values that work? Yeah, all the way down to -10. Because like, what's -9 squared? 81. That's still within. That's still that square is still less than 100. What else? All right, I want to go to this last one because it's a little bit of a different representation. But I want to find this integral. Is this an integral you can take using things that we did before last week? How many people are kind of thinking arctangent something? I'll bring it up. Is this integral, can I just directly call this an arctangent of something? How so? So we just dealt with this. The derivative of arctangent or inverse tangent of x. Yeah, so basically let's look at this first. So if we know the derivative of arctangent of x is 1 over 1 plus x squared, right? Could I adapt that to deal with this 1 over 1 plus x to the 7th? One over 1 plus x to the 3.5 squared. That's true, right? So I mean, whether or not you were thinking this, you kind of set up a u substitution, right? If that's u, what's du? Right. I don't think that u substitution is going to help us because we don't have that. Like we don't have an x to the 5 halves or x to the 2 halves or x 2.5 somewhere else, right? So because of that, I don't think the u substitution, I don't think any of those kind of direct approaches are going to help here. But is there a way for me to make 1 over 1 plus x to the 7th look a little simpler? So this didn't work, but am I allowed to represent this as a power series? How come? I mean, I can see that as a geometric sum. So let's start representing it as a power series. What does 1 over 1 plus x to the 7th look like? Let's look at some terms. What's the first term? 1. What's the next one? Negative x to the 7th. And then? Like this, right? So because of what we've done in the last few class periods, we know that those two things are identical. Or not identical. They're equivalent. Which means I have no idea what this integral is. But could I integrate this? What is that integral? Okay. So I think that's so we got the first 3 terms. Now what? I mean, really, isn't this the answer? We asked for an integral of that function, and I think by first writing that as a polynomial, or like an infinitely long polynomial, we got that answer.
You don't need to write out the function.
I mean, technically we have. I mean, that's what this is that I've boxed in. We can't write out all the terms, but we can. That's what we're gonna ask for now. Can we do that? Or would it be more helpful if we did this? Should we write out the summation notation for this first? Good. So I think that's a good representation for the original, or for like inside that the function that was inside the integral. So then what's a good sigma representation for the antiderivative of it? Does this work? Should we test a few terms? When n equals 0, does that sigma notation give us the thing we actually want? Looks like it gives you x. What about when n equals 1? Negative 1 to the 1 times x to the 8 over 8. Seems like it works. Either one of the two things I boxed in are the integral.
Like I'll press up and put either one in.
Depends on how WebWork asks for it. Sometimes it wants the coefficients of the first several terms. Sometimes it wants like the definition of the thing in sigma notation, but yeah, be ready for either one. How we doing? Okay. You ready to be done talking about this section? Fine. But we only have a couple minutes left, so I'm going to stop here. And we'll pick up the last section of the chapter next time.